Our last lecture covered the difference between ionic, covalent, and polar covalent bonds. As a reminder, ionic bonds are those in which the electronegativity difference between the items that are bonded is very high. Covalent bonds are when the electronegativity difference between the two elements is very low, and polar covalent bonds have an intermediate difference in electronegativity between 0.4 and 1.8. Molecular compounds, which are the topic of Chapter 5, have either polar covalent or covalent bonds. Ionic bonds belong in Chapter 4 with ionic compounds. This is a chart that shows percent ionic character versus electronegativity difference. As you can see, electronegativity difference is on the x-axis and percent ionic character is on the y-axis. The mostly ionic materials are in the upper right, where we have sodium chloride, potassium chloride, rubidium fluoride. So these would be metals bonded to nonmetals in an ionic type bond. Things that have covalent bonds, you may notice, are mostly nonmetals or hydrogen, like carbon with hydrogen, carbon with oxygen, silicon with chlorine. There are some exceptions. For example, silver with chlorine appears to be a metal-nonmetal combination. Actually, it's a mostly covalent bond because silver, although a metal, has a very high electronegativity, much like the nonmetals. Often, a person can use distance on periodic table to determine electronegativity values. For example, if we look at a compound between magnesium and fluorine, boron and fluorine, or potassium and fluorine, notice that potassium and fluorine are the furthest apart on the periodic table, so they would be the most polar combination. Magnesium and fluorine are a little bit closer, and of course, boron to fluorine is very closely located on the periodic table, so we would expect that to be the least polar type of bond. This question asks us to rate the relative polarity of the following bonds from least polar to most polar. Now, when hydrogen is involved, sometimes that can be a little bit tricky because hydrogen is not exactly a metal, not exactly a nonmetal. So in this case, it's helpful to look up the electronegativities. This electronegativity chart is available in your textbook, and if I scroll down, you can see some of the values. Hydrogen is 2.2, carbon 2.6, oxygen 3.4, and bromine 3.2. Let's go back to our question. So let's put the value of 2.6 below each of the carbons. 2.6 here, 2.6 here, and 2.6 here. Bromine is 3.2. So the difference in electronegativity between 2.6 and 3.2 is 0.6. Oxygen's electronegativity is 3.4. So the difference in electronegativity is 0.8. Hydrogen has an electronegativity of 2.2. So the electronegativity difference is 0.4. Now, sometimes students get a little confused about this because they think, well, shouldn't the 0.6 and the 0.8 be negative and the 0.4 be positive? No. We are looking at the absolute values of these numbers. So, 0.4 is the lowest. That puts carbon and hydrogen at the least polar, so certainly not answer B. The next polar is carbon and bromine, followed by carbon and oxygen. So I do believe this should be answer C. This question asks, which way does the polarity arrow point? And remember that the tip of the arrow is going to be toward the most electronegative. So between carbon and fluorine, I think you have probably memorized that fluorine is more electronegative. So that is correct for that choice. So we know it's not B. Between carbon and chlorine, well, hopefully you've sort of memorized also that chlorine and nitrogen are the third most electronegative elements on the periodic table. So pointing toward chlorine is indeed correct. So let's see. Definitely not answer C. Okay, so now we are down to, is boron more electronegative or carbon more electronegative? Well, let's check the periodic table. On the periodic table, we can see boron here at element number 5 and carbon at element number 6. Which one is more electronegative? If you said the one further right, which would be the carbon, you would be correct. Carbon is more electronegative than boron. So, as carbon is more electronegative than boron, I do believe we need to go with answer D. The next part of this lecture covers naming compounds. And as a reminder, for ionic compounds, we're concerned about the oxidation state. So whenever we have a metal and a nonmetal, or a polyatomic, this is a reminder that the cation name is typically unchanged for groups 1, 2, and aluminium. And if we have a monoatomic anion, the ending is -ide. If we're involved with a polyatomic, we can just go with aluminium sulfate. Transition metals, we should definitely give the oxidation number for all but the few exceptions. And heavy metals, we should also give the oxidation number. And in this case, we can have a polyatomic as the anion. For molecular compounds, these are things where a nonmetal is bonded to a nonmetal. So we can actually say how many. The convention is to have the least electronegative atom first and the more electronegative atom second. So we have a prefix with the first and a prefix with the second with an -ide ending. An example is combinations of molecules with nitrogen and oxygen. There are 3 well-known compounds. The first one, which is N2O3, we're going to use prefixes with. So we will say that is dinitrogen trioxide. The second one would be dinitrogen monoxide. The third one would be nitrogen dioxide. One does not use the mono prefix when there is only one of the first element. But notice we did use it for N2O because there was one of the second element. You're probably already pretty familiar with the prefixes for the number of atoms. Mono is for when you have one atom, and I'm sure you've heard of carbon monoxide. Di is for 2 atoms, carbon dioxide. Tri would be for 3 atoms. Phosphorus trichloride is an example. Tetra would be for 4 atoms. So carbon tetrachloride might be an example that is sometimes used in dry cleaning. Penta, well, you know that a 5-sided shape is a pentagon. So how about phosphorus pentafluoride? A 6-sided shape, that's a hexagon. So how about disulfur hexabromide? And then there's hepta, octa, nona, and desa. Hepta we sometimes encounter as tetraphosphorus heptoxide. The other ones, octa, nona, and desa, you'll more than likely see in organic chemistry. So the trick to naming some of these is to determine first if they're ionic or molecular, and then apply the correct naming convention. So let's look at SO3 with no charge. So no particular charge on this. This would be a molecular compound because it's composed of sulfur and oxygen. So how about if we call this sulfur, and then there's 3 oxygens, so trioxide. That seems good to me. Okay, the next one has chromium in it. Chromium is a metal, so I think I have to name this as an ionic compound. Sulfur, I would guess, would probably be -2 for each sulfur, since it's underneath oxygen. That would give me a chromium charge of +6. So I would have to call this chromium, CHROMIUM, 6, and sulfide. Okay, the next one with sodium in it, I think we can effectively decide that that's ionic. So I will go with sodium for my metal. Do I need any Roman numerals? I don't think so, because sodium's in column 1, so we know it has to be +1, which means this other polyatomic, BrO2, has a charge of 1-. So then we need to go through our naming conventions for oxoanions in group 7. That is bromine with 2 oxygens and a -1 charge. That is going to be the bromite ion. So this is sodium bromide. Selenium and chlorine. Selenium is a nonmetal. Chlorine is a nonmetal. So we will call this a molecular compound. So I will call this selenium dichloride. Okay, chlorine and oxygen, also both nonmetals. So I will name this as a molecular compound. There are 2 chlorines, so that would be dichlorine. And 7 oxygens, so hept. And usually when we have 2 vowels, we drop the A, so heptoxide, not heptaoxide, is good. And remember, we're leaving the first one as is, dichlorine, and the second one gets an "ide" ending. Magnesium with SO3. Magnesium, that's a metal, so we know this is an ionic compound. Magnesium is going to be +2. It's in group 2, so I do not need any Roman numerals. Magnesium. No 2 needed. Now, if magnesium is +2, this polyatomic ion here must have a 2- charge. So SO3 with a 2- charge. If you go back to your naming conventions, I hope you realize that this is going to be a sulfite. Finally, we have NH4S. Now, initially, sometimes students think this is molecular because nitrogen's a nonmetal, fluorine's a nonmetal, hydrogen is an honorary nonmetal, so hey, it must be a nonmetal. But be careful. Whenever you see NH4, remember, that is a particular cation. That is the ammonium cation. So this is indeed an ionic compound, and we would call this ammonium and then fluoride. And that would be how we name that. So let's go through some questions. Phosphorus with 5 chlorines. Do you think that's an ionic or a molecular compound? I'm hoping you think it is molecular. So you get to say how many. So no oxidation states needed, that's for sure. And I see there are 5, and pent seems like a good answer for 5. So how about phosphorus pentachloride? Okay, next one. Lead. Lead is a metal, and it's a transition metal. So I think I need to name this as an ionic. And probably I need to know the oxidation states, right? Because lead would be one of those heavy metals. I think this NO2, I sort of recognize it as being maybe a polyatomic with a -1 charge. So that means I think the lead has a +2 charge. So let's get rid of these at least. We know that's not it. Ooh, lead dinitrogen dioxide. Oops. that seems very silly. Let's not do that. So, let's see here. I see these two are the same choices. Whoops, I thought I fixed that one semester. But I do know that this is going to be lead with a 2 charge and that this is the nitrite ion. And we do not need to say di. Remember, ionic compounds are all about oxidation states. Okay, next one, selenium with fluorine. I think those have got to be molecular. So let us get rid of anything that has Roman numerals. We don't need any of that. And let's see, 6 fluorines. So not hept, right? My goodness, I think I like diselenium hexafluoride. Does that look good to you? I hope so. Okay, our next part of this lecture is to start talking about Lewis symbols and how we put them together to make molecules. The number of dots around each element symbol is going to be the number of valence electrons. So as you might guess, anything in column 1 has 1 valence electron. Anything in column 2 will have 2 valence electrons, and so forth. So really what we're more interested in here is the nonmetals right here and knowing how many valence electrons are available to bond. So when you try to build a compound, the object of the game is to have an octet of outer electrons in the shell. So one way to do this is to make an ionic compound. And in this way, metals are going to lose valence electrons, nonmetals are going to gain valence electrons, and both will become isoelectronic with a noble gas, which has 8 electrons in the outer shell, except for helium. Sharing valence electrons, which is what happens when nonmetals are bonding together, we have to do something different in order to get 8 electrons around each atom. Now, there is an exception to what's known as the octet rule of getting 8 electrons around each atom. Hydrogen's nearest noble gas is helium, so hydrogen would like to have 2 electrons around it, a duet of electrons. So let me try and demonstrate to you what you would do if you were going to try to build the chlorine molecule. Chlorine, as you know, is in group 7. So each chlorine atom has 7 dots around it to exhibit 7 valence electrons. So if we were going to make each chlorine feel like it had 8 around it, we would have to share 2 electrons. So if I draw a circle around the chlorine on the right, you can see that it feels like it has 8 electrons around it. It has the 7 electrons it brought in, plus the 1 it's sharing. The same thing with the chlorine on the left. If I draw a circle around the electrons surrounding it, it has access to 8 electrons. So what we're essentially doing is counting the 2 electrons in the middle twice. These are known as bonding electrons or shared pairs, and the electrons that don't bond are known as lone pairs or non-bonding electrons. And this would be the Lewis structure of Cl2. Except we would, instead of drawing 2 dots between the chlorines, we would typically draw 1 line to represent 2 dots. So how do you determine the Lewis structure for molecules? There's a set of recommended calculations that you can do that actually will speed things up if you're unsure of what the structure is. Your first job is to determine how many electrons each atom in a molecule needs for an octet, or a duet if it's hydrogen, if nobody's shared. This calculation is known as electrons required. And don't worry, I'm going to demonstrate how to do this in the next few slides. The next calculation is known as valence electrons. That's determining how many electrons you actually have to work with. So it's the sum of the atom's group numbers minus the charge on the molecule. Next is determining how many bonds or shared pairs you have, and that is 1/2 the electrons required minus the valence electrons. And we can also determine how many lone pairs we have. and that's 1/2 the valence electrons minus 2 times the shared pairs. Then we write our atoms on the paper. First atom of a formula is generally the central atom. So connect your atoms with the number of shared pairs that have been calculated. Fill in the electrons around these atoms until everyone, except hydrogen, has an octet. Remember, an atom with 1 bond needs 3 pairs of electrons. 2 bonds needs 2 pairs of electrons, and 3 bonds needs 1 pair of electron. Look at your molecule. Count the number of electrons. You should only have the sum of the valence electrons and the charge. Formal charges, we'll worry about that for the next lecture, so don't worry about that quite yet. Alright, so let's say we want to make the Lewis structure of phosphorus with 3 fluorines. The first calculation is electrons required. There are 4 atoms in this compound. 1 phosphorus, 3 fluorines. So that's just 4 times 8, 32. Next is valence electrons. So phosphorus is in group 5, right? That's where we get the 5 from. Each fluorine is in group 7, and there's no charge on the molecule, so a 0. So that gives us 26 electrons. All I'm going to do now is take 32 minus 26. That gives me with 6 electrons that I have to share, and dividing that by 2 gives me 3 bonds. Now, what about lone pairs? Well, remember, we have 26 electrons to play with. If 6 of them are in bonds, then 20 of them must be in not bonds, which are known as lone pairs. So dividing 20 by 2 gives me 10 lone pairs. All right, phosphorus goes in the middle because it's the first element listed in this compound. We put the fluorines around it. We are going to attach with 1, 2, 3 bonds. Now we just have to fill in the electrons. Fluorine has 1 bond to it, so at the moment it thinks it has access to 2 electrons, so it needs 6 more. Now you can see that fluorine has 6 electrons around it and 1 bond. That gives it 8 electrons. The next fluorine also needs 6 electrons around it and the 1 bond to have 8 electrons. And the last fluorine also needs 6 electrons around it. What about the phosphorus? The phosphorus has how many electrons around it right now? Well, it's got 3 bonds, so that means it has 6 electrons around it. It just needs 2 more. Now let's look at our structure. We had 26 electrons to play with. 26. Are there 26 in this structure? Well, let's see. 2, 4, 6, 8, right? A bond counts as 2. 10, 12, 14, 16, 18, 20, 22, 24, 26. Yes, 26 electrons are in this structure. 10 lone pairs, 3 bonds. What about formaldehyde? Well, electrons required, remember we have 2 hydrogens, and those like 2 electrons around it, so that's where the 2 times 2 comes from. And we have 2 non-hydrogens, the carbon and the oxygen, so that's where 2 times 8 comes from, 20 electrons. How many electrons do we really have to play with though? 4, that's for carbon. 1 for each hydrogen, 6 for the oxygen, 0 because it has no charge. So we have 12 electrons to play with. 20 minus 12 gives us 8, divided by 2 gives us 4 bonds. As far as non-bonding electrons, 12 minus 8 is going to give us 4, so we'll need 2 lone pairs. All right, let's put the carbon in the middle and the hydrogens around the sides, and the oxygen on top. Everybody gets 1 bond, and hydrogen's really pretty happy with 1 bond. 1 bond means hydrogen has access to 2 electrons. So once we stick a bond to hydrogen, we're pretty much done. But that oxygen could take another bond, so we'll put another bond between the carbon and the oxygen. All right, what about lone pairs? Well, my carbon's pretty good, right? My carbon has 4 bonds around it, So I don't need to add anything more to my carbon. And I don't need to add anything more to my hydrogens. But my oxygen has 2 bonds around it. That means only 4 electrons. So I think it needs 2 more pairs, or 4 electrons, to give it a total of 8 electrons. So when I look at this structure, I've used my 4 bonds, and I've also used my 12 electrons in such a way that each hydrogen sees 2, and carbon and oxygen each see 8. Here are the Lewis structures for diatomic gases. Now, if you were asked to draw the hydrogen molecule, I don't think you'd go through all this math. But if you did, it works out. You will get a single bond between hydrogen atoms. If you wanted to draw the Lewis structure of oxygen, the diatomic gas, you would wind up with 2 bonds between the oxygens. And that's the way in which each oxygen would have access to 8. If you did this for nitrogen, you would discover that, oh, I need 3 bonds between the nitrogens in order for each one to have access to 8 electrons. So that brings us to the discussion of bond order. Bond order is the number of bonds divided by the number of bonding regions. A bonding region is an area of electron density between 2 atoms. So much of the time, bond order is as it appears to be to your eye. The hydrogen molecule has bond order 1. The oxygen molecule has bond order 2. And the nitrogen molecule has bond order 3. That brings me to a discussion of differences that bond order can cause in the structure. So this is the Lewis structure of ethane, and I am doing this simply so that you can see that if you were to draw this out, you would have a carbon-carbon single bond. This is the Lewis structure of ethylene. And I do this simply so you can see when you draw it out that you would have a carbon-carbon double bond. This is the Lewis structure of ethyne. And in this, you would have a carbon-carbon triple bond. So let's get these all together on the same slide. As you can see, every time we lose 2 hydrogens, we gain a double bond. And we can see that the first one is bond order 1 between the carbons, the second one bond order 2 between the carbons, and the third one bond order 3 between the carbons. It turns out that a carbon-carbon single bond has a length of 1.54 angstroms. A double bond is shorter. It has a bond length of 1.33 angstroms, and a triple bond is shorter still at 1.20 angstroms. Also, the bond energy, or energy required to break a bond, is different dependent on bond order. For a carbon-carbon single bond, it takes 347 kilojoules per mole to break that bond. It takes 612 kilojoules, more energy, to break a double bond, and 820 kilojoules, which is more energy still, to break a triple bond. So, within a series of bonds between the same atoms, the higher the bond order, the shorter the bond, the stronger the bond, the higher the bond energy. Several years ago, I actually had a student who said, hey, you could demonstrate this in a really easy way. And he explained to me what he thought would be a nice demonstration. So, as I cannot show you this in class, here it is. Here's 2 students holding a rope between them. This is a single thickness rope. The connection between them is weak, and the distance is long. But what if they were to double up that rope, fold it in half? Well, you notice their connection would be stronger, right? They'd have the strength of 2 ropes between them, and the distance between them would be shorter. Well, what if they folded that rope yet again? They tripled the rope. As you can see, they would have the strongest length of rope between them and the shortest distance. So I think you can see, single bond, double bond, triple bond, stronger and shorter as we up the bond order. So this brings us to our last question. Choose the structures with the longest end-to-end and the strongest end-to-end bond. And I trust that as you look at these structures, you say, okay, that's got bond order 1, that's got bond order 3, that's got bond order 2. So let's see, which one would be the longest? The lowest bond order, right? So it's got to be either answers 1, 2, or 3. Which one would be the strongest? The triple rope, of course, right? So structure B. And this concludes the lecture.